Hello students, welcome to physics class of PU2. So in the previous class we have discussed about the chapter atoms. So in the chapter atoms we have discussed in the previous class about the energy level diagram of hydrogen atom and the spectral series of hydrogen atom, and also one of the important point, we have derived the expression for the wave number of emitted light in a spectral series of hydrogen atom, and that is also called as what the Rydberg formula we have derived it, that is 1 by lambda is equal to r into 1 divided by n1 square minus 1 divided by n2 square, where r is the Rydberg constant, its value is 1.097 into 10 to the power 7 per meter, and n1 and n2 are different for different transition. So we have 5 series in hydrogen spectrum, that is the first one is what Laminar series, Laminar series, Patchen series, bracket and P-Fun series. So in this way we have 5 series we have explained in the spectral series of the hydrogen atom. Right, now we have to use this formula and we have to solve the certain numericals based on the chapter atoms. Right, now for Laminar series the transition is, we have to explain here, that is for Laminar series n1 is equal to 1 and n1 is equal to 2 for Balmer and n1 is equal to 3. Laminar Balmer and Patchen series, and n1 is equal to 4 for bracket and n1 is equal to 5 for P-Fun series, and the n2 are what, the higher energy states. There is a specific transition we have to explain. Now let us solve certain numericals here based on this Rydberg formula, that is what, the calculate the shortest and longest wavelength of the Balmer series of hydrogen atom. The shortest and longest wavelength of the Balmer series of hydrogen atom we have to calculate. So in the previous class I have drawn the energy level diagram for this. Right, what is mean by shortest wavelength and longest wavelength here? That also I defined one term here. What is mean by series limit? What is mean by series limit? Right, if N2 is equal to infinity, that is the last transition, that is called as the series limit. So as I have drawn what the energy level diagram for a spectral series of hydrogen atom, right? N is equal to 1 here, right? N is equal to 2, N is equal to 3, and N is equal to 4, and so on. And finally, what we get here, N is equal to infinity. So for Balmer series, that is 1 by lambda is equal to 1 divided by lambda is equal to r into 1 divided by n1 square minus 1 divided by n2 square. For Balmer series, this n1 is equal to 2 here. That is n1 is equal to 2. n1 is equal to 2 for Balmer series. Now, shortest wavelength. What is meant by shortest wavelength and longest wavelength? Shortest wavelength means what? Wavelength of the line is inversely proportional to the energy. As we know that E is equal to h nu, right? Or mu is equal to what? C by lambda. So energy is inversely proportional to wavelength. So what is meant by shortest wavelength means what? Shortest wavelength means the energy is highest. Energy ಜಾಸ್ತಿ ಇರ್ತದೆ, wavelength ಕಡಿಮೆ ಅಂತಂದ್ರೆ energy ಜಾಸ್ತಿ ಇರ್ತದೆ. So ಅಂದ್ರೆ ಯಾವುದು ಟ್ರಾನ್ಸಿಷನ್ ಆಗ್ತದ್ರಿ ಇಲ್ಲಿ? For shortest wavelength, the transition is from what? Infinity to seconds. Right? Shortest wavelength means what? The transition is from infinity to n is equal to 2 for the Balmer series. The last transition ke ಏನಾಗಿದ್ರೆ energy ಜಾಸ್ತಿ ಇರ್ತದೆ. So ಹಾಗಾದ್ರೆ longest wavelength ಅಂದ್ರೆ ಏನಾಗ್ತದೆ? Longest wavelength ಅಂದ್ರೆ energy ಕಡಿಮೆ ಇರ್ತದೆ. Higher the wavelength, lower the energy. ಹಾಗಾದ್ರೆ ಯಾವ ಟ್ರಾನ್ಸಿಷನ್ ಎನರ್ಜಿ ಕಡಿಮೆ ಇರ್ತದೆ? ಫಸ್ಟ್ ಟ್ರಾನ್ಸಿಷನ್, ರೈಟ್? ಸೊ ದಟ್ ಈಸ್ ವಾಟ್ n1 is equal to 2 and n2 is equal to 3. n1 is equal to 2 and n2 is equal to 3. So this is what the longest wavelength. This is longest wavelength. So N1 is equal to 2 and N2 is equal to infinity. N2 is equal to infinity. This is shortest wavelength and highest energy. So in this way you have to identify the specific N1 and N2 for different transition and for different series, Lyman, Balmer, Preston, bracket and Friedman, and then you have to calculate the wavelengths here. I think this is very simple point. You have to understood this. Right? Shortest wavelength means what? Shortest wavelength means the last transition. That is also called as what? The series limit. Shortest wavelength. That means what? Highest energy. Right? Shortest wavelength means what? The highest energy. Now, longest wavelength means what? Lower energy. That is the first transition. The last one is called as the series limit, and this is the first member of the series limit. N1 is equal to 2 and N2 is equal to infinity. This is the first member of the Balmer series, and N1 is equal to 2 and N2 is equal to 3. It is the series limit or last member of the Balmer series. Now let us solve this problem here by taking N1 and N2 for shortest wavelength and longest wavelength. Okay, for shortest wavelength of the Balmer series, as now I explained, N1 is equal to 2 and N2 is equal to infinity. Now calculate the wavelength of the line. That is the series limit, the wavelength of the last transition in Balmer series. Therefore, wavelength 1 divided by lambda is equal to R into 1 divided by N1 square minus 1 divided by N2 square. Right? So 1 divided by lambda is equal to R value is 1.097 into 10 to the power 7. Right? 1 divided by N1 square. That is 1 divided by 2 square. That is equal to 4. Right? 1 divided by N1 square. 2 square is 4 minus 1 divided by infinity square. That is infinity. Therefore, this is equal to 1 divided by infinity is 0. 1 divided by infinity is 0. So this is equal to 1.097 into 10 to the power 7 into 1 divided by infinity is 0 and it becomes 1 divided by 4. 1 divided by 4. This is 1 by lambda. Therefore, 1 divided by lambda is equal to 1.097 into 10 to the power 7 divided by. Therefore, lambda is equal to what here? Reciprocal of this. That means what? This is what? 1 divided by lambda. Now I want the lambda here. Wavelength I want. Shortest wavelength I want. So reciprocal of this, that is equal to 4 divided by 1.097. 1.097. So into 10 to the power 7 here. I write it in the numerator. So it becomes into 10 to the power minus 7. So 4 into 10 to the power minus 7 divided by 1.097. So what is the value of 4 divided by 1.097? So 4 divided by 1.097, its value is what here? 3.646. Its value is 3.464 into 10 to the power minus 7. Now I want to write this value in terms of nanometer or in terms of angstrom, right? So if you want to write this in terms of angstrom, so it becomes lambda is equal to 3464. So I taken 3 digits to the left side. So 10 to the power minus 3 into 10 to the power minus 7. So it is equal to into 10 to the power minus 10 meter. So it is the wavelength. So unit is meter. So this value can also be written as what? The lambda is equal to shortest wavelength is equal to what here then? 3464 angstrom. 3464 angstrom. So this is the shortest wavelength of the Balmer series. That is the wavelength of the last transition, last wavelength. Now let us similarly solve here the wavelength, the longest wavelength of the Balmer series. So similarly, as the same way you have to solve here, N1 is equal to 2 and N2 is equal to 3. Therefore, 1 divided by lambda is equal to R value 1.097 into 10 to the power 7. 1 divided by 4 minus 1 divided by 3 square is 9. So 1 by 4 minus 1 divided by 9. You have to solve this bracket. 1 by 4 minus 1 divided by 9. What is the value you will get here? 1 divided by lambda. 1.1 divided by lambda is equal to 1.097 into 10 to the power 7. Now if you solve this bracket and we're taking the LCM, so you will get the value 5 divided by 36. 5 divided by 36, that is the value of this bracket. Take the LCM and solve it, you will get 5 divided by 36. Now this is 1 divided by lambda, therefore the value of lambda is equal to what here? 36 divided by 5 into 1.097 into 10 to the power minus 7, right? Into 10 to the power minus 7. So if we solve this, 36 divided by 5 into 1.097, solve this, we will get 6563 angstrom. So this is the wavelength of the first member of the Balmer series. That is the longest wavelength of the Balmer series. So in this way you have to solve the numericals based on the Rydberg formula. So similarly, now I have calculated here the shortest and longest wavelength of Balmer series. In the same unit, we calculate Laminar series, Pascal series, bracket and Pepin series. So this is the homework for you. You have to calculate the remaining 4 series, shortest wavelength and longest wavelength. So note down this numerical. This is very important numerical on the chapter atoms, and this problem is asked in the March 2016. In March 2016 annual examination, this problem is asked for 5 marks. So they may ask other series for other series also. So for that's why you calculate the Lyman, bracket, Pepin and Pascal series. So all the remaining 4 series is the shortest and longest wavelength you calculate. Now let us take the one more problem. So this problem is asked in the annual examination March 2017. The first member of the Balmer series of hydrogen atom has a wavelength of 6563 angstrom. Calculate the wavelength and frequency of the second member of the same series. It is the Balmer series, and the given value is here C into 10 to the power C is equal to 3 into 10 to the power 8 meter per second. So this value is given to calculate the frequency, because nu is equal to C by lambda. First we have to calculate the wavelength, then we have to calculate the frequency. Right. For the first member of the Balmer series, so first member here, for first member of the Balmer series is the value of N1 and N2. The value of N1 is equal to 2 and the value of N2 is equal to 3. Therefore, the 1 by lambda is equal to 1 divided by lambda is equal to R into 1 divided by N1 square minus 1 divided by N2 square. This is our Rydberg formula. For first member, 1 divided by lambda is equal to 1 divided by lambda is equal to 1 point. I will keep it the value of R as it is, right? Then we will see what happens in the next point. So 1 divided by N1 square minus 1 divided by N2 square, right? For first member N1 is equal to 2 and N2 is equal to 3, right? This is equal to what? N1 square 4 minus N2 square is 9, right? So again solve this by taking the LCM. So it is 36 and then 5 by 36 we will get by taking the LCM, and by solving we will get 5 by 36. Therefore this is 1 divided by lambda is equal to 5R divided by 36. Call this as equation 1. For second member, again for second member, what is the value of N1 and N2? N1 is equal to 2, it is same. N1 is equal to 2 and N2 is equal to what here? 4. For second member of the Balmer series, N2 is equal to 4. Again 1 divided by lambda is equal to R into 1 divided by 4 and 1 divided by 6. Therefore 1 divided by lambda is equal to R into, so solve this bracket again by taking the LCM, and by solving we will get 3 divided by 60, or this can be written as 1 divided by lambda is equal to 3r divided by 16. 3r divided by 16. Now call this as equation. Call this as equation. Now divide the equation 1 by 2. Dividing equation 1 by divide equation 1 by 2. So what you will get, then equation is 1 by lambda is equal to 5r by 36 and 1 by lambda is equal to 3r divided by 16. And the value of lambda is given here. The value of lambda is given here for the first member of the Laminar series, that is 6563 angstrom. So this is equal to 1 divided by 6563 into 10 to the power minus 10. So this is equal to 5r divided by 36. Call this as equation 1. Call this as equation 1. Now therefore dividing this equation by this equation, that is 1 divided by 6563 into 10 to the power minus 10 divided by 1 by lambda, equation 1 by 2, and this is equal to 5r by 36 divided by 3r divided by 60. 3r divided by 60. So again this goes to numerator. So lambda divided by 6563 into 10 to the power minus 10, and this is equal to 5r divided by 36 into 16 divided by 3r. So here r and r get cancelled here, and 16 divided by 36 here. So that also we can calculate here. 16, this is what, 4 4s are, and this is 4 9s are. So you will get what, lambda divided by 6563 into 10 to the power minus 10, and this is equal to what we can write. So this is equal to what we can write here, 5 into this is equal to 5 into 4. This is equal to what, 20 divided by 9 into 3. Now again solve this. So by solving this, we want the value of lambda here. Therefore lambda is equal to, taking this to the RHS, 6563 into 10 to the power minus 10 into 20 divided by 9 into. Therefore by solving this, we will get the answer. What here? 4861 into 10 to the power minus 10. So this is the wavelength of the second member of the Laminar solution. Now we can calculate the frequency. Nu is equal to C divided by lambda. 3 into 10 to the power 8 divided by lambda is 4861 into 10 to the power minus 10. So again by solving this, we will get the answer 6.17 into 10 to the power it is equal to 14 10 to the power 14. So this is the value of frequency, and this is the value of wavelength of the second member of the Laminar series. Now in this way you have to solve based on the calculation of frequency as well as the wavelength. The next point we have to discuss here about the limitations of Bose atomic model. So already we have discussed the postulates of the Bose atomic model. We have derived the expression for the radius of the stationary orbit, nth stationary orbit, and the expression for the energy of an electron in the nth stationary orbit. And now we have to see what are the merits and the demerits of the Bose atomic model here. And the limitations. Limitations means what? The drawbacks also we can call it as. The limitations means drawbacks. And this is a very important question for 3 marks on the chapter, the atoms here. So let us see first one, the limitations of Bose atomic model. So Bohr's atomic model successfully explains about the neutrality of the atom, and also it explains about the stability of the atom, and also it explains about the spectra of simple atoms. It explains about the spectra of simple atoms. That means what? It is applicable for what? The first one. This theory is applicable for hydrogen and hydrogen-like atoms. So this is the first limitation. The Bohr's atomic model, this theory is applicable only for hydrogen and hydrogen-like atoms. This Bohr's atomic model explains only the spectra of simple atoms. That means what here? The atoms having only one electron. Hydrogen atom is what? It is having only one electron. It is having only one electron. It explains about what? The spectra of simple atoms. That means what? The atoms having only one electron. And it can explain the spectra of hydrogen atom and hydrogen-like atoms. That means what? Hydrogen atom, you know what is meant by hydrogen-like atom? Hydrogen-like atom means what? It is having only one electron. Hydrogen, helium, right? Helium is not hydrogen-like atom, but helium plus singly ionized helium. So one electron tagidre helium helium plus that means what? It is hydrogen-like atom. The spectra of helium plus is explained by what? The Bohr's atomic theory. And also what? Lithium, doubly ionized lithium. Lithium atomic number is 3, right? The atomic number of lithium atom is 3. Now if you remove the 2 electrons, so it becomes what? Lithium plus plus. Doubly ionized lithium, singly ionized helium. So these are what? Hydrogen-like atoms. So helium plus is also hydrogen-like. Lithium plus plus is also a hydrogen-like atom. So in this way, this theory is applicable only for hydrogen and hydrogen-like atoms, and Bohr's theory it explains about the spectra of these simple atoms, and it fails to explain the spectra of complex atoms. Right? It fails to explain the spectra of complex atoms. That means what? The atoms having more than one electron. It fails to explain the spectra of the atoms having more than one electron. More than one electron is out of the spectrum due to the transition. Adana explain only this explains about the what? The spectra of the hydrogen and hydrogen-like atoms. The next point, it fails to explain the relative intensity of spectral lines. So it fails to explain what? The relative intensity of the spectral lines. So one line kuma innondu line the intensity ಬಗ್ಗೆ comparison is ಮಾಡೋದಿಲ್ಲ. That means what? It fails to explain the relative intensity of spectral line. So this is the second limitation of the Bohr's atomic model. It fails to explain the fine structure of spectral lines. What is meant by fine structure of spectral lines here? So when the spectral lines of Laminar series, if we observe under the powerful microscope, what happens? It consists of what? Closely spaced line. Now Laminar series anna high magnified microscope ತಗೊಂಡು observe ಮಾಡಿದಾಗ ಏನು ಕಾಣಿಸ್ತದೆ ನಮಗೆ? So ನಾವು single line ಹೇಳಿದ್ವಿ, but ಅದರ ಜೊತೆಗೆ closely line is closely aligned space ಯಾವುದಕ್ಕೆ ಬರ್ತಾವ ಅನ್ನೋದನ್ನ ಇದು ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡ್ತೀವಿ. It fails to explain what? The fine structure of spectral lines. When we observe the Laminar series under a powerful microscope, what we observe there, the spectral line, single spectral line consists of what? Again a closely spaced lines, and this Bohr's model would not explain about these fine structure of spectral lines. So this is one more limitation of what the Bohr's atomic model. Next, it could not explain the Zeeman effect and Stark effect. It fails to explain what? The Zeeman effect and Stark effect. What is meant by Zeeman effect? We are going to study it in the higher classes, but just I give the definition of what the Zeeman effect and Stark effect. So Zeeman effect means what? The splitting of spectral line in the presence of magnetic field. That is called as the Zeeman effect. So for example, if one spectral line ಬರ್ತದೆ, ಅದನ್ನ ಸೋರ್ಸ್ ನಾವು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ದಾಗ ಇಟ್ಟು ಅಂದ್ರೆ ಏನಾಗ್ತೈತ್ರಿ? ಒಂದು ಲೈನ್ ಇದ್ರೆ ಎರಡು ಮತ್ತೆ ಏನಾಗ್ತೈತ್ರಿ? ಸ್ಪ್ಲಿಟ್ ಆಗ್ತದೆ, right? This is called as Zeeman effect. This original line lambda brother, but when we kept the source in the magnetic field, under the magnetic field, what we get here? The splitting of spectral lines in the presence of magnetic field. That is called as what? The Zeeman effect. So ಇದು lambda ಅಂತ originally ಒಂದು lambda plus d lambda ಅಂದ್ರೆ ಇನ್ನೊಂದು lambda minus d lambda. So ಈ ರೀತಿ ನಮಗೆ ಮತ್ತೆ ಎರಡು ಎಕ್ಸ್ಟ್ರಾ ಲೈನ್ ಬರ್ತವೆ. ಆ ಎಫೆಕ್ಟ್ ಏನಂತ ಕರಿತೀವಿ ನಾವು Zeeman effect ಅಂತ. So in the presence of electric field ಈ ರೀತಿ ಆಯ್ತಂದ್ರೆ ಅದನ್ನ ಏನಂತ ಕರಿತೀವಿ ನಾವು ಸ್ಪಾರ್ಕ್ effect. The splitting of spectral lines in the presence of electric field is called as spark effect. The splitting of spectral lines in the presence of magnetic field is called as the Zeeman effect. So ಇವತ್ತು ಬಗ್ಗೆ ಇದು explain ಮಾಡೋದು Bose theory. So this is one more limitation of what? The Bose atomic model. Again, it could not give any indication regarding the arrangement and distribution of electrons in it. So ಯಾವ ರೀತಿಯಾಗಿ electrons arrangement ಆಗಿರ್ತವೆ, distribute ಆಗಿರ್ತವೆ ಅನ್ನೋದ್ರ ಬಗ್ಗೆ ಇದು ಯಾವುದೇ ರೀತಿ ಇಂಡಿಕೇಶನ್ ಕೊಡಲ್ಲ. ಯಾವ ರೀತಿಯಾಗಿ electrons ಅನ್ನು ವೇರಿಯಸ್ ಆರ್ಬಿಟ್ ಒಳಗೆ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟ್ ಮಾಡಬೇಕು ಅನ್ನೋದನ್ನ ಇದು ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡೋದು. It could not give any indication or the information about the arrangement and distribution of electrons in an atom. So these are the important limitations of the Bose atomic model. So in the examination you may get this question in the 3 marks. So you have to write any 3 limitations for 3 marks. Suppose if they are asked in 2 marks, you have to write any 2 limitations. So you may get 5 mark question. Write the postulates of Bose atomic model and then write its limitations. So you can write any 2 or 3 limitations for 2 and 3 marks, right? So this is about Bose theory and Bose atomic model and the limitations of Bose atomic model and its merits also we have discussed, right? Next one of the important and last point in the chapter comes, that is the de Broglie explanation of Bose's second postulate of quantization. So Bose's second postulate of quantization tells us what? The angular momentum of an electron revolving in a stationary orbit, allowed stationary orbit, is equal to what? Integral multiple of h upon 2 pi. So we know that according to both postulate of both second postulate of quantization of angular momentum, right? What we have to write here? mvr is equal to n into h upon 2 pi, or this we can write 2 pi r is equal to n into h upon m into but what is the h upon m into v, right? The de Broglie wave equation, what we have done, lambda is equal to h upon p or p is equal to m into v, right? The wave nature of electron, right? So here the de Broglie established the connection between the wave nature of electron and the stable orbits of the Bose atomic model, right? This lambda is equal to h upon p. Therefore 2 pi r is equal to what we can write here? 2 pi r is equal to h upon mu is equal to what? N into lambda. So this is the 2 pi r is equal to n into lambda. This is very important point given by what? The de Broglie here. What does it mean here? According to de Broglie, the circumference of the orbit of the electrons, the circumference of the orbit of an electron is equal to integral multiple of electron wavelength. As the electron is revolving around the nucleus in a certain stable orbit, in which the circumference of the orbit is equal to, according to de Broglie, the circumference of the orbit of the electron is equal to integral multiple of electron wavelength. So this is the de Broglie quantization of the second postulate, de Broglie explanation of Bose's second postulate of quantization. The Bose postulate ಏನು ಕೊಟ್ಟಿರ್ತಾನೆ, why the angular momentum of an electron is equal to n into h upon 2 pi ಇದೇನು ಕೊಟ್ಟಿರ್ತಾನೆ, ಈ ಅದಕ್ಕೆ ಏನಾಗ್ತದೆ, ವೇವ್ ನೇಚರ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ ಇಲ್ಲಿ ಕಂಪೇರ್ ಮಾಡ್ತಾರೆ. ಸೊ ಯಾವಾಗ ಎಲೆಕ್ಟ್ರಾನ್ ಇಲ್ಲಿ ರಿವಾಲ್ವ್ ಆಗ್ತಿರ್ತದೆ ಸ್ಟೇಬಲ್ ಆರ್ಬಿಟ್ ಒಳಗೆ, ಅದು ವೇವ್ ನೇಚರ್. So here the wavelength of the electron is equal to the integral multiple of wavelength. The circumference of that stable orbit ಎಲೆಕ್ಟ್ರಾನ್ ಯಾವ ಆರ್ಬಿಟ್ ರಿವಾಲ್ವ್ ಆಗ್ತಿರೋದ ಅದರ ಸರ್ಕಂಫರೆನ್ಸ್ ಯಾವುದಕ್ಕೆ ಈಕ್ವಲ್ ಆಗಿರ್ತೈತ್ರಿ the integral multiple of wavelength of the electron that is revolving in its stable orbit. So this is called as the wavelength of the electron. This is one wavelength of the electron. So in this way n times of wavelength is equal to what? The circumference of the orbit. So this is what the de Broglie explanation of Bohr's second postulate of quantization. So he just given the relation, or he given the relation between what, or the connection between what, the wave nature of the electron and the stable orbit, or orbit circumference ka ಮತ್ತು wave nature of electron ka ಅವೇನ್ ಮಾಡ್ತಾನೆ ಇಲ್ಲಿ ಕನೆಕ್ಷನ್ ಕೊಟ್ಟು ಇದನ್ನ ಎಕ್ಸ್ಪ್ಲನೇಷನ್ ಹೇಳ್ತಾರೆ. 2 pi r is equal to n into lambda. Circumference of the orbit is equal to the integral multiple of the wavelength of the electron. So this is very important point here. 2 pi r is equal to n into lambda. This is derived from what? The Bohr's second postulate. Hence it is called as what? The de Broglie explanation of Bohr's second postulate of quantization. Okay. Okay, I'll stop here. Thank you, students.